In the Surenexus project, we begin with a co-creative, participatory process in which diverse stakeholders define the core assumptions. From those assumptions, stakeholders and modelers collaboratively develop the diagrams that will ultimately produce the models. This approach creates a validation feedback loop between modelers and stakeholders, ensuring everyone understands and accepts the assumptions used throughout the process. Specifically, sessions begin with the definition of a conceptual model using the specification and description language, SDL. SDL is a graphical, complete, and unambiguous language standardized by the IEUT, suitable for specifying simulation models and, in particular, the digital master component of a digital twin. Once the conceptual model is defined in SDL, SDLPS, a simulation tool with native SDL support, can execute the models. SDLPS is highly versatile but requires technical expertise, so it is not directly accessible to all stakeholders. To simplify interaction, the model is deployed on the Nakata website and exposed only through parameterization. A user-friendly interface permits non-technical users to run scenarios and adjust parameters without needing to work with SDL directly. The results produced by the simulations can be applied to improve system behavior. Because the underlying assumptions remain explicit in the SDL diagrams, stakeholders can inspect and revise them as new information or improvements arise, increasing confidence in and the adaptability of the models. Therefore, focusing on the tools developed by the project's different actors, we produce a set of complementary deliverables that work together to ensure model quality. First is the conceptual model, created in specification and description language, SDL, which provides a formal, graphical specification of the system. Second is the assumptions document, a textual record that enumerates and explains the key assumptions underpinning the model. Finally, continuous validation and optimization are performed through ongoing system monitoring and analysis, for example, leveraging the Nakata infrastructure to validate, refine, and update both the model and its assumptions over time. On the Nakata website, a stakeholder can view the most recently executed model, for example, the KKL demo site running a specific experiment. Each experiment includes a set of configurable parameters. Among these, compensations are key variables used to parameterize alternative solutions intended to improve system behavior. Compensations are technological measures or process changes that balance exchanges of energy, water, ecosystem services, or waste among system components to reduce overall impact. Below are some of the compensations defined and developed during the Surenexus project and already implemented on the Nakata website. We can compare compensations to highlight differences in their characteristics, enabling a quick assessment of which features are relevant for a new scenario or to evaluate each compensation's effects. By systematically juxtaposing attributes such as expected performance, cost, resource exchanges, energy, water, ecosystem services, waste, and temporal dynamics, stakeholders gain a clearer understanding of trade-offs and synergies among options. On the Nakata site, we can browse projects and select a specific experiment. Selecting an experiment lets you define all input parameters: the building, the chosen compensation, climate files, and farm-specific settings. Farm settings are provided as CSV files that list parameters such as crop types, area, irrigation schedules, fertilization rates, and other management practices. Each set of parameters, building, compensation, climate, and farm CSVs, is uploaded to the experiment and visible in the experiment definition. These CSV inputs are then used to run the simulation and evaluate the experiment's effect on production. From the compensations defined in the database, we can select any subset to include in an experiment. After running the experiment with those selected compensations, the simulation produces the results needed for analysis and decision-making. Presented as a tree, the experiment's parameters can be reviewed hierarchically, showing each input group and its individual fields. This view makes it easy to verify that all required parameters, building, compensations, climate files, and farm settings, are present and correctly configured. By expanding branches, you can inspect values, Identify missing or inconsistent entries. Once the experiment finishes, the results are available for download as CSV or R data files, and key charts and visualizations can be viewed directly on the Nakata website.